Need to debug why your FastMCP server isn't recognizing valid JWT tokens, or just want to see exactly what claims are being passed in each request? We'll build a simple token inspection tool that extracts and decodes the JWT from incoming requests, giving you full visibility into the authentication context without breaking the existing verification flow. This pattern works alongside any Scalekit or OAuth provider, so you can debug issues or log user claims in production.
From FastMCP server context, import request CTX. Import JWT. At MCP, tool. Def inspect token, dict. Inspect the current JWT token claims. Context equals request CTX, get. Hash extract token from authorization header. If hasheader, context, request, and hasheader context, request, headers. Auth header context, request, headers get authorization. If auth header starts with bearer, token equals auth header 7. Hash decode without verification, already verified by provider. Claims equals JWT. Decode, token options equals verify signature, false. Return claims. Return error, no token found.
This demonstrates the token inspection pattern in authenticated systems, where middleware validates credentials while application code examines claims for context. The approach separates security enforcement from business logic, letting you inspect verified tokens without handling cryptographic validation yourself. What makes this distinctive is its reliance on pre-verified tokens, treating authentication as a solved problem while exposing only the claims your application needs. The pattern works by leveraging the existing authentication pipeline. The framework validates the JWT signature, issuer, and expiry before your code runs, so you can safely decode the payload without verification. This creates a clean boundary. Infrastructure handles security, while your tool focuses on extracting and using identity or permission data from the token claims. The separation keeps security concerns out of your business logic, while still giving you access to user context. This approach matters because it solves the common problem of needing user context without reinventing security. You avoid writing token validation code, reduce attack surface by using framework-validated tokens, and still get access to claims like user IDs or scopes. It's particularly useful in microservices, API gateways, or any system where you need to make authorization decisions based on token contents, but want to keep security logic centralized and maintainable. The trade-off is framework dependency, but the benefit is significantly reduced security boilerplate. Let's break it down line by line.
From FastMCP server context, import request CTX.
This imports request CTX, FastMCP's context manager for accessing request-specific data. It provides the current execution context, including headers and authentication details, which this tool needs to inspect the JWT token.
Import JWT.
Imports the JWT library for JSON web token operations. This enables decoding the JWT from the authorization header to inspect its claims, which is essential for token validation and debugging.
At MCP, tool. Def inspect token, dict. Inspect the current JWT token claims.
This defines an AI callable tool using FastMCP's decorator pattern. The function extracts and inspects JWT token claims, while the decorator exposes it to AI models with automatic schema generation from the type hint and docstring.
Context equals request CTX, get.
This fetches the current request context from FastMCP's thread local storage. The context contains all request-specific data, including headers, which we need to inspect the JWT token.
Hash extract token from authorization header. If hasheader, context, request, and hasheader context, request, headers.
This is defensive attribute checking. It verifies the context object has both a request and headers before proceeding, preventing attribute error crashes if the structure is incomplete. Common pattern when working with dynamically constructed objects like web requests.
Auth header context, request, headers get authorization.
This extracts the authorization header from the request, defaulting to an empty string if missing. Standard HTTP header access pattern that safely handles absent headers, preventing key error exceptions.
If auth header starts with bearer.
This checks for the bearer token scheme in the authorization header, the standard format for JWT authentication. Without this prefix check, any malformed auth header could trigger invalid token processing, creating unnecessary errors. The pattern follows RFC 6750 for HTTP authentication schemes.
Token equals auth header 7.
This slices off the bearer prefix from the authorization header, isolating the raw JWT token. The 7-character offset skips past the fixed bearer string, a standard OAuth 2 convention for token transmission.
Hash decode without verification, already verified by provider. Claims equals JWT. Decode, token options equals verify signature. False.
This decodes the JWT token without signature verification, trusting the provider's prior validation. The verify signature, false option skips cryptographic checks since the token was already authenticated by the API gateway or auth middleware. This is a common pattern when working with pre-verified tokens in trusted environments.
Return claims.
This returns the decoded JWT claims to the caller, completing the inspection. The early return pattern here ensures we exit immediately after successful token processing, avoiding unnecessary checks. This matches FastMCP's tool contract, where functions must return serializable data for AI consumption.
Return error, no token found.
This is the fallback return for when no valid JWT token is found. It handles the error case gracefully by returning a structured error response instead of raising an exception, which prevents crashes in the calling system. This pattern ensures API consumers get consistent, predictable responses even in failure scenarios. FastMCP token introspection pattern. This tool demonstrates how to inspect JWT claims after FastMCP's authentication. Layer has already verified the token signature, showing the separation between verification and claim inspection. The verify signature equals false. Option is only safe because FastMCP's authentication provider has already validated the token's cryptographic integrity. Always handle missing headers gracefully, as not all requests will include authorization tokens.
The token that reveals everything knows nothing of itself.